We are going to start polar coordinates today. We're going to do a few funky graphs. We're going to do one by hand and then we're going to do them on our calculator. This ties very closely to vectors. So we could have done it in the vector chapter. That's where I've done it in the past, but it's actually part of chapter 11, so I went ahead and just left it until now this time. It ties together some of what we've been doing with vectors. All right. The main idea here to start out is that, oh, I don't know what that is. It's not on my screen. Go away. Stop. Okay. Has anybody seen this graph paper before? These graphs? Okay. This is used by things like air traffic controllers because they they want to know at what angle from either it's off of north, we're going to do off the positive x-axis, from the landing place, strip, whatever you want to call it. They're going to measure some angle, and then they want a distance out to where this person is. Okay? So they want to know that at 302 degrees and out 40 miles is plane A. Okay? And plane B is at the same angle, but it's further out or something, okay? Or closer in or whatever. Obviously, they don't want them to be on top of each other, okay? This is called polar graph paper. These, if this is 90 degrees, can you figure out what these angles would be in here? Well, this would be 45, right? Thanks. Vincent, this is you. This would be 45, and it's split into 3 parts, so each one of these lines is what? 15, 30, 45, 60, 75. Are we okay? Okay. The idea today is that we need to be able to convert back and forth between rectangular and polar coordinates, and then we're going to do a little graphing. The basics relationships we're going to use are these. These should all look familiar. See if anyone spots the typo. X squared plus y squared equals r squared. Just Pythagorean theorem, right? Okay, where r is going to be the distance out here, x and y are going to be the x and y coordinates. Cosine equals x over r, which we multiplied it across this way to get this for vectors. Remember that for vectors? This? Yeah. This should be inverse tangent of y over x. Good catch. Okay, that is going to be to find the angle theta that we've rotated around. All right, again, this is 11.5 in your book. If you struggle with some of this, you may want to read that. All right, the coordinate system most commonly used is a rectangular coordinate system, which is based on 2 perpendicular axes. However, other coordinate systems are possible. The thing is, when we graph in the rectangular coordinate system, if I say go over 4 and up 3, everybody in this room is going to find the same spot if it's the same size graph paper, right? There's one name for that spot. In polar graphing, there are multiple names for the same place. Think about that for a second. If I tell you to rotate around 90, we didn't talk about what these circles are yet. This is out a radius of 1. This is out a radius of 2. Does that seem okay? Okay. But I could tell you to rotate around 90 degrees and go out 2. But couldn't I also tell you to rotate around negative 270 and go out 2 and you'd land at the same place? Okay. So it will have multiple names. Right, the polar coordinate system uses a pole. The origin is called the pole. Like, I don't know, the North Pole or what, but it's called the pole. Okay, the horizontal ray extending to the right is called the polar axis. It ends at the origin here, or starts at the origin and goes out this way. A point P is given by the radius, the distance out, and then the angle. This is backwards to me, okay, because you have to rotate first and then go out, but that's the way it's written. All right, the theta coordinate, the rotation around is either positive off the x-axis or negative. We're used to that, right? Clockwise, counterclockwise, this is counterclockwise, is positive. The polar system imposes a circular grid on the plane, and the polar coordinates of P are not unique. There's multiple ways to name the same point. So, here we go. Okay, when you are doing polar to rectangular, you're going to do r cosine theta and r sine theta, sound like vectors. Okay, when you're going rectangular to polar, you're going to use Pythagorean theorem and inverse tangent. All right, let's try this out. This means we need to rotate around from the polar axis over here in a counterclockwise direction 150 degrees. So these are 15, so it would be 10 of those, or 150 would be here. Does that seem right, guys? 30 back from 180, okay? Now, this would be 1 unit out right there. Does everybody see where my dot is? It's on that first little circle. We're supposed to go 4 units out, so I'm gonna erase that guy. And I'm gonna go on that line out 1, 2, 3, 4. I'm gonna put kind of a big dot so you can see, and that's gonna be A. We rotated around 150 degrees and then went out 4. In a minute, we're gonna have to come up with another name for that, because there are multiple, really infinite names for that spot. Okay, B says 3, negative 90. What do you think? Any ideas? Yep, rotate down here. Okay, negative 90 degrees, so this will be our negative 90. And go out 3, 1, 2, 3 would be here. Make sure you count this first one. Sometimes I forget. Okay, that one's 1, this is 2, this is 3 units. All right, C is at 2, 5 pi over 4. Yes, these can be measured in radians. Okay, 5 pi over 4 is 5 45-degree angles. 1, 2, 3, 4, 5, or it's 225 if you want to convert. And it's out 2 units. 1, 2. Okay, right there. Now, this next one is the weird one. Everybody okay? Anybody lost yet? All right. This is rotate around 30 degrees. It's like you're standing at the origin and you've turned your body 30 degrees. This negative 2 means literally step backwards kind of a thing. 2 units. Okay? So after I turned 30 degrees, I was facing here, but this negative 2 tells me to back up 2. So it's going to be back over here. It's actually just 1 line over from C. Mine is really hard to see. And that's D. That's the tricky one that students struggle with. Are we okay? You went around a positive direction. Could we have a negative negative, guys? If I'll do an easy one, okay? Negative 1, negative 180 degrees. It just means you're going to rotate around this way to negative 180, but the negative 1 then would mean back up, so you go over here. Okay? Negative, negative. All right. We need to come up with a second name for every point over here. Any volunteers for point A? We said 4, 150. Anybody have another name? Noah? Ooh, he's getting really complicated right off the bat. Let's see if that works, guys. 330 is what you said, right? So go around 330, which would be 30 from being done, so that would be here. And then back up backwards 4. Does that work? Yeah. He made it about as complicated as you could on the very first try. Nicely done. All right? He's the one whose paper I don't want to have to grade because he's going to go for the hardest answer possible. B, 3, -90. Guys, B is right down here. What else could you call B? Oh, somebody's going to be nice to me. 3, 270. We could have gone with radians, I suppose. That's an easy one, right? 3 pi over 2. Okay. What about C? C is right over here. We originally said 2, 5 pi over 4. We go 2, 225. Could you do a negative angle? How much is it negative? Okay, we could do negative 135 or negative 3 pi over 4 if you wanted radians. All right, anybody brave enough to try a negative for D? It's kind of tricky one for D. If I had gone this, okay, please listen. If I had gone this direction around, but I was going to back up, I would have had to go all the way over to here, right? So I'd be on this axis, which is negative 330. And then I backed up to D, I would back up how many? Negative 2. Now, the only reason I want to do different variety here is, in the book, there is a problem on the bookwork that says, by the way, the bookwork assignment is listed at the top of your worksheet, I think, isn't it? Right at the top or not? No? Okay, then you have to write it down off the board later. It's page 742. The bookwork has a section where it gives, I think I only signed like 2 problems, but it says, give 4 other names for this same point. One that has a positive negative, one that's negative negative, one that's negative positive, and whatever, okay? Got it? All right. We're going to this section. Let's just plot this point real fast. Can you tell me what this would be if I go in rectangular coordinates, across 0 and up 1, I'm right there. What would that be if I started drawing circles on my paper? I went out 1, and I went around 90 degrees, or pi over 2, or negative 270, lots of choices, right? Okay? Guys, this gets more complicated very quickly, so please be paying attention. Negative 3, positive 3, went left 3 and up 3, and I need to know R and theta to get me to that point right out there. Okay, x squared plus y squared equals r squared is what we're going to use. Does somebody recognize that if you went left 3 and up 3? It's a 45, 45, 90. So does anybody know what the special right triangle, the length would be on the hypotenuse? 3 square roots of 2, okay. If you did Pythagorean theorem, are we all okay? So we went out 3 square roots of 2, and you just told me the angle was a 45 in here, so what could we call all the way around there? 135 degrees? How would we have to do that if we didn't know? Do you remember? We know this side and this side, so we would do second tangent of 3 over negative 3. Try that on your calculator. Is it going to give you the right answer? It gives me negative 45 degrees. How do I know that something's wrong with that answer? I could actually use negative 45, but then I'd have to back up. This is not the right quadrant, right? Remember, second sine, second cosine, second tangent only give you one quadrant answer, so there's a possibility that you're in the wrong quadrant. If it gave you this, you would have to add 180 to it to get the 135, okay? Let's try C. Again, this is really much easier if you know the special right triangle. It is a 30, 60, 90. If you go over 6 and down 6 square roots of 3, I made that not very proportional, but does anybody remember? This would be the short leg, the long leg, and the hypotenuse. This is 60 degrees in here, and it's 2 times the short leg, so this is 12. I'm going to do Pythagorean theorem just so we're sure we get this. This would be 36. This would be 36 times 3, which is 108, which is 144. So when we square rooted, everybody would get 12. Are we good? Okay. Anybody have a name right now that you would like to do? 12,300. Does that work, guys? Could I call it 12 negative 60? Okay. If I typed second tangent of y over x, can everybody type that, please, and tell me what you get? Does it give you a usable answer or not? If you put the negative in, doesn't it give you negative 60? Is that in the right quadrant, that negative 60? It's in the fourth quadrant, so it would be okay to use that answer? Or to add 360, which is the positive 300, either one. All right. Got to use a little logic here. Now, I'm not sure if this is good news or bad news, but these aren't special right triangles, so we can use decimals, okay? So how did we find the distance out? 5, 7, we did Pythagorean theorem.
Yeah.
We could leave it exact if you wanted, but 5 squared plus 7 squared equals, okay, square root of 74, which is 8 point something, between 8 and 9, okay? No? 7, okay. Thought I was having a moment there. And how are we going to find this angle in here? How about inverse tangent of what? 7/5, y over x, okay? What do we get?
54.4623.
Okay, I'll go 54.5.
Okay.
All right, can you guys try E? And check if you get the right quadrants for your angle. You can give me a decimal for the R, I really don't care. What quadrant is that landing us in if we go -2, -3? So when you did inverse tangent, did you get something that would land you there? Okay. It gives you, this angle is 56.3 degrees in here. If we want to go all the way to the third quadrant, we'd have to add 180. Does anybody know what the other option would have been? Can anybody think about that? Yes, because you get a negative one. Yeah. What if you just said, what if you said I went positive 56 degrees, but then I did what? I went backwards. So I could have said -3.6. What does it come out, guys? No? 236, did I add right?
Yeah.
Oh, it's 0.3, isn't it?
Yes.
Okay. All right. The other possibility, please stop chatting, is that we have to go the other direction. Okay, I'll put 10 of these on the next test, okay? This says you rotated 60 degrees and never took a step. So where are you at? Which is 0, 0 in XY coordinates.
So we get 10 of those.
The next one says you rotated around pi over 2 and took 4 steps out. What is that in terms of an XY name? These are polar names. I need an XY name. That's okay. 4 pi over 2 and 490 degrees are equivalent in polars, but we want an XY. All right. 3 negative pi over 2 is down here and out 3. So what would that be? Okay. We did no work whatsoever because we're lazy. Okay. Let's go back. Actually, those are in radians, so they're a little painful anyway. Let's try the next one. This one says r is 6 square roots of 3 and theta is negative pi over 3. How do you find x and y? What's the little rule that we were just doing in our head? We didn't know it. Anybody know what we were really doing here? No, I always want to write those parentheses. All right, at 60 degrees, you're multiplying by 0, so it didn't matter. Here, this is 4 times, well, the coordinates here for cosine and sine were 0 and 1. So this was 4 times 0, comma 4 times 1. The coordinates down here are what? On your unit circle, this is 0, negative 1. So the cosine is 0. So this was 3 times 0 and 3 times negative 1. All right, I need you to be on your unit circle. Can you find negative pi over 3 for me? Negative 60 degrees or 300. What's the sine and the cosine? Is that correct? You okay, Gunther? All right, the radius out to here is 6 square roots of 3. So the rule is we're going to take 6 square roots of 3 times the cosine, comma, 6 square roots of 3 times the sine. All right, we need to do some simplifying. This would be 6 square roots of 3 all over 2, which would be what? All right. And this is 6 square roots of 3. Oh, I lost my square root. I don't know what happened to it. Sorry. What's square root of 3 times square root of 3? 3 times 6 is 18. Divided by 2 is? This should be negative 9. All right, let me back up and talk about special right triangles. Negative pi over 3 is a negative 60 degrees. What's wrong with this? Normally when you have a 30, 60, 90, across from the 60 is a square root of 3, right? If you remember those at all, you have to take half of the hypotenuse to get the short leg, and then you have to take the short leg times a square root of 3. Well, is that what we did? We got 3 square roots of 3 and negative 9. Is this equivalent to 9? Yeah, it was just going down, so it was negative. All right, we're going to try it again. We're going to try it again. We're going to use our unit circle. Everybody have their unit circle? r is 5 square roots of 2, and theta is 3 pi over 4. We are supposed to do r cosine of 3 pi over 4, and then r sine of 3 pi over 4. What is the cosine at 3 pi over 4? That's multiplying, okay? And the sine at square root of 3 over 4? It's positive square root of 2 over 2. How is that going to simplify? 5, square root of 2 times square root of 2 is 2, and then we're dividing by 2, so that all just becomes what? Negative 5. 5 square root of 2 times the square root of 2 is 5 times 2, divided by 2 is 5. Let's see if that made any sense if we just thought about it a minute. 3 pi over 4 is over here at 135 degrees. If you went out 5 square roots of 2, and this is a 45-degree angle, shouldn't both the legs be 5? But you went left and up? Okay. The easy ones, and this you could have actually done in your calculator, you would have had to be in radians, but F is the easy one, guys. What do you have to do on F? What have we been doing for all these that we now could just type in our calculator because it's nothing that's on our unit circle? What was I using? Are you just not making up stuff? I'm using this. So we're going to do what? Going to type 10 cosine of 50 degrees and then 10 sine of 50 degrees. Tell me what 2 decimals you get quickly.
First one, 6.4.
Okay, are we in the right quadrant if we rotated 50 degrees? We're in quadrant 1, so positive, positive is right. We're done. All right, moving on. You're going to need to refer to those examples when you get to this. All right, this is a question I want to do by hand, and it does not go well generally for students, but we're going to do it quickly by hand. I want you to type into this equation in degree mode these numbers really fast. 1 minus 3 times the cosine of 0. Anybody? Okay. 1 minus 3 times the cosine of 30. One point what?
6.
Okay. 1 minus 3 cosine of 45. Did you do 1 minus 3 cosine of 30?
I have 1 minus 3 times cosine of 30, I got 0.5.
Are you in degrees?
I am. Sure. Oh, you read it. I got
Next one's negative 1.1.
60? Anybody do 60?
Negative 1.5.
Negative 0.5? 90? Positive 1?
Yep.
120? 180? 240? 270? 300?
Negative 0.5.
And 360? Negative 2? Okay. You will notice that this started going 0, 30, 45, 60, 90, and then we started skipping around a little bit over here. Went 120, but there's no 135, 150, we just skipped. If we put all the points on, it would be even better, but I'm going to show you roughly what happens. You know what? Just watch. Just watch. It'll go so much faster, okay? And then you can sketch it on your paper. Just watch. Turn from here 0, so I'm facing this way, but I back up 2, right? Are we okay with where I'm starting? Go around 30 degrees, which is 2 of these, back up 1.6, 1.5, and connect this with a smooth curve. This is go around 45 degrees, back up 1.1, connect with a smooth curve. 60 degrees is to this one, back up half a unit, which is here, connect with a smooth curve. Now this is where we started skipping some, well, in a minute here, okay. 90, we're all the way out at 1, right there. Does everybody see that that's 91? Okay? All the way over there. 120 would be 90 plus 30. So this one, we're out 2.5. 1, 2.5. We're out here. 180, we're out at 4. 1, 2, 3, 4. 240, which is 180 plus 60 is this guy. We're at 2.5. 1, 2.5. Okay. 270, we're at 1 unit out. 300 is this one, right? Backing up a half a unit, so we're over here again. And 360 is back to this line, but we're backing up 2, which is actually here. Okay. This is the shape we're getting. Okay. Go ahead and sketch that. It goes through -4 over here and -2. Just do a little sketch on there, and then we'll talk about how to do it on your calculator. And that shape does have a name. We'll talk about those from the book in a minute. All right, are you ready to try the calculator? Okay, I need you to put your calculator, go to mode. It's a big day, guys. Remember at the very first day of class, I told you that there is function, parametric, polar, sequential, and that first week we did sequence mode and you thought we were crazy? Okay, have we done a few parametrics? Okay. We're actually going to do more parametrics next week, but you get to use polar mode for the first time. You want to be in degrees and then go down here to polar. Function, parametric, polar. On polar, hit enter. Mode, degrees, and polar. Now go to your y equals button. Your y equals button, it suddenly says r equals. Does everybody see that? Okay. Brennan, you good?
No, I have it on polar, now what do I do?
Go to y equals.
Oh, yeah, no.
Does it say r?
Yeah.
Okay. Now, we want to type in 1 minus 3 cosine. Oh, that mine didn't get a minus. And instead of x, this button right here, remember at the beginning of the year we talked about, it has x, t, theta, and n. In sequence mode, it gave us an n. Guess what it's going to give us in polar? Theta. So go ahead and hit that. Now, just like in parametric mode, you have to be careful about steps. I need you to go to the window, and I need you to just listen very closely. There's a lot of stuff in this window. Okay, I want you to do one rotation, so go 0 to 360 because we're in degrees. I think it pops up in radians on your calculator. It says 0 to 6.28, which would be 2 pi. We're in degrees, so put 0 to 360. For this step, that's how many times do you want it to calculate? Don't put anything smaller than 1 there, just because if you put a 1, it's 360 calculations. I put a 5 there. That's plenty of calculations, okay? Otherwise, it just bogs your calculator down a long time. Now, at first, I just did -5 to 5. You can put scale of 1 or you can leave it, doesn't matter. And then I did -5 to 5 for the y's by a scale of 1, and I graphed. It's actually stretched out because of your calculator screen. So if you wanted to see what it actually looks like, if you did a zoom square, after you did that, it would square up your window a little bit, and you would see that it is circular. All right, one more thing. If you go to second and then zoom, you get the format. If you want to see the rectangular coordinate or the polar coordinates, under format, second, zoom, go over to polar and hit enter, and then go back to your graph and hit trace and scroll around a little bit. It's giving you r theta down at the bottom. Mine's counting by fives because that's what I told it to. Every click would be 5, because that was my scale. Or my step, I'm sorry, my step. Anybody's not working? Okay. I want you to go back to y equals and type in the next question. I'm missing the next 2 slides for some reason. What is the next equation, guys? 4 sine theta. Delete all the rest of this out of here. Okay. If I hit graph, I get a circle. Does anybody remember how much fun it was to try to graph a circle in the past? It was like the square root of 36 minus y squared and the negative square root, or minus x squared, and the opposite of the square root of 36 minus x squared. Some crazy business, okay? Okay, can you sketch this one quickly, please? This is it should be a circle that is 4 units across. So on your polar graph paper, I'm going to graph it on the same picture because my graph paper, I don't have the slides for some reason for those 2, and I tried to find them and it didn't go well for me. Right here, 1, 2, 3, 4, there's the other end of my circle, and it is a perfect circle. Yep, mine's not, but it's supposed to be. Okay, and the next one that you have on your paper is 2 sine, oh, we're getting to the fun stuff, 3 theta. Okay. If you trace out on this one, okay. Sorry, trace. This is actually at 30 degrees, the tip. So if I'm drawing it on my graph paper here, it would be at the 30. And then over here, it would be at the 30 over there and straight down here. And the length of those little petals is 2 units. All right, I'm going to give you 1 minute to play around here, and then we need to move on. But I want you to see what happens. Look, if I change that 2 to a 5, the same 3 petals are 5 times as long. Now watch what happens. If I change that 3 to a 4, because it's even, I actually get 8 petals. If I change it to an odd number, like 5, I get 5 petals, which isn't going to be as smooth. Okay? Fiddle around for a second if you want. You got 60 seconds. We are doing this, guys. We were playing around with this. You put in a number here for A and a number here. If you want to try... If you want to try a different shape, you can try some of these equations. You want to try a spiral? Try putting in like 3 theta. Just 3 theta. Yeah, it goes off the screen. Yeah, it goes shooting off the screen. I have to think about what you'd have to do there. I think you'd have to go... I don't remember how you get a spiral. I think you just have to go around more rotations. Like if I made this 1,000. Okay, your time's about up. And then I zoomed way out. Because it doesn't have quite as much purpose in life. I did a spiral, but it's still too big. I don't know how to make it fit on the screen better.
100 data.
Yeah, I did 100 by 100 for my window, but, okay. Shh. I need you to put down the calculator and look up here. All right. The easiest way to graph a polar function is to use your graphing calculator in polar graphing mode. Otherwise, it's very tedious and painful, okay? The following is a summary. Please look up here. You do not have this in your notes. If you use this, where theta is greater than 0, you get a spiral going around this way. Less than 0, you get a spiral going around this way. I was having trouble making it fit on the window. I don't know. I'd have to play around with it. I don't remember that much about those. This one, okay, if you put a number in here and do 1 minus theta, you get a cardioid. It looks kind of like a heart, rounded heart. Look, I want you to notice the symmetry. This one has a cosine in it, and the symmetry is with which axis? The x. This one has a sine in it, and the symmetry is with the y-axis. All right? A sine here gets you symmetry only in one dimension. It's not, it has an odd number of petals. I don't know what I'm trying to say here. And if you put in a cosine, get an even number of petals. Actually, I'm not sure that's right. I think the number you put in has to do with how many petals you get. And like I showed you, the circle is just a cosine or a sine. Again, cosine has symmetry with the x, sine has symmetry with the y. This one, lemniscate, I don't know, I'm not saying it right, it's French. Get an infinity symbol if you put in a negative and then a number squared times sine of 2 theta or cosine. This is the one we did to begin with. It's, I believe, pronounced limousin. It's French again, limousin, I'm not sure. That's what we got this little thing with that looks like a cut open lima bean to me, I don't know. All right. We need to talk about some of these. We're getting a little further than the last period did. This is on the next page, okay? Think about what this means. All points where r is equal to 2. Noah says it's going to be a circle where the radius is what, Noah? 2. You can type it in if you want, guys. It will not look like a perfect circle on your screen unless you have a square window. That's the picture. Now, to convert this, everybody looking up here? I know you want to fiddle with your calculator. To convert this, it says r equals 2. If we square both of those, we get r squared equals 4. Didn't lose anybody yet, right? What did we say r squared was equal to a few minutes ago? X squared plus y squared, Carolyn said. Is that the equation of that same circle? 0, 0, radius of 2. So that's what goes on this blank. And that's what we got for a graph. Everybody okay? Yes.
Do you have another one of those? I have the wrong file.
It would be up here in that pile, okay?
Correct.
The next one says r times 3 cosecant theta, or you could type 3 divided by sine. Anybody try that one? Type r. What do you get? It is a line, isn't it? Okay. We are going to, it says hint, multiply to eliminate the fraction and trade. All right, right now it says r equals 3 over sine theta. I want to multiply the sine over to that side. I should have written it not with a sideways fraction bar. If I multiply that over there, I get r sine theta equals 3. What is r sine theta? You've been telling me since the vector chapter. R sine theta is equivalent to y. Guess what you just graphed? the line y equals 3. Number 3, we're trying to go backwards, okay? This one's kind of wacky. I'm not going to ask you to do this without some hints, okay? This one is kind of wacky. It says x equals r cosine theta. So put in 2r cosine theta plus y, well, y is r sine theta, equals 4. What can I factor out? I need to get the r by itself, okay? So it will say r times 2 cosine theta plus sine theta equals 4. If you divide all that over there, you'll have r by itself. 4 over 2 cosine theta, close parenthesis, plus sine theta, close parenthesis, and you'd need the whole denominator. Before you leave, I want you to type that in and see if you get a line that looks like that 2x plus y equals 4. 4 divided by, parenthesis, 2 cosine theta plus sine theta.
I got
Okay.
yeah.
Yeah, it's really weird how it does it because it's actually rotating it around. But it goes this way. And then it comes back this way, doesn't it? But did it cross here? My sketch is really bad. Did it cross at 2 right here? And 4 up here?
Yeah.
Okay, does that seem like the right line for y equals negative 2x plus 4? Okay, so wait a minute. The circle was really nice in polar, but is the line nicer as a line in xy or as a polar? This equation looks much nicer, right? The rectangular form of the line is much nicer, whereas the polar form of the circle is much nicer. All right, be sure you write down page 742 bookwork, please. Here, it's up on the screen if you need it. Okay, there it is.